first manned mission through deep space is about to reach its final destination, Mars. The crew must now prepare for the most dangerous stage of this perilous expedition, landing on the surface of the red planet.
Entry descent landing is obviously the most complicated because it's the most death-defying portion.
We are go for Mars entry. Stand by. In 3, 2, 1.
Once you start the entry, descent and landing through the atmosphere, there's no turning back.
And when you go, and you go all the way to the surface. It's very scary. It happened really quick because going from the outer top of the atmosphere of Mars to the surface is only about 6 minutes.
For entry, descent, and landing, we are roughly...
The Americans have dubbed landing on Mars the 6 minutes of terror. 6 long minutes when all the controllers and astronauts can do is wait and pray that everything does what it's supposed to.
On your way in and you lose your heat shield, you have a problem with your heat shield, that's the end of your mission. It's got to work. It's got to work the first time.
2, 1.
Aeroshell malfunction.
Fire the rockets! Firing rockets! We've lost guidance!
We have one shot to get it right. Their lives are in our hands.
Landing on Mars is a complex 3-stage process. Entry, descent, and landing. Stage 1 starts when the lander enters the Martian atmosphere, 125 kilometers above the surface, and lasts about 2 minutes. The spacecraft is hurtling towards the surface at 16,000 kilometers an hour, 20 times the speed of a jumbo jet. Friction heats the air around the outer skin to 4,000 degrees Celsius. So hot, the lander appears to be cutting through the atmosphere like a blowtorch.
You're basically burning a hole through the sky on Mars, ionizing the atmosphere as you move through it, and punching a hole of burnt ionized gas. And that hot gas is looking constantly for methods of getting into cracks and burning the rest of the spacecraft up.
The only thing that's keeping the crew from being roasted alive is the aeroshell, a protective shield that's covered with a heat-resistant skin.
Columbia, Houston, UHF comm check.
The fatal accident of Space Shuttle Columbia in 2003 was a deadly reminder of what can happen if the heat shield fails.
We are only acquiring false locks at this time. I copy, Fido.
Since that day, engineers around the world have been working on new kinds of armor to protect the crew. Neil Cheatwood is an atmospheric entry systems expert at NASA's Langley Research Center in Virginia.
What I'm standing in front of is the command module of the Apollo 12 flight. This is a capsule with a heat shield on it, because when you come into the Earth's atmosphere at very high speeds, you generate a lot of heat.
This heat shield saved the lives of the Apollo crew re-entering Earth's atmosphere. But the Martian atmosphere poses a much bigger challenge.
It's kind of the worst of both worlds. Mars has not enough atmosphere to land like we land a spaceship on Earth, but too much atmosphere to land like we do on the moon.
Apollo 11, this is Houston. How do you read?
When we landed on the moon, we had a landing system that was designed to land on a body that has no atmosphere. And so we could come up with a shape that's just totally functional for the landing system. And so if you look at the lunar lander, you can see the legs hanging off of it. You can see fuel tanks and stuff because it didn't have to be aerodynamic.
The lunar module had an outer surface about the thickness of a can of Coca-Cola. Very, very thin. And that's not enough protection. On Mars itself doesn't start at the surface, it goes way up. There's all this atmosphere. It's still only 1% of Earth's. That's enough for it to create a huge amount of heat as the vehicle screeches through this atmosphere.
But this heat shield has a second critical job. While protecting the crew during the firestorm of entry, it will also double as a brake. And that's a big job, because this lander will be a monster compared to anything that's ever landed on Mars before. In 1976, NASA successfully landed 2 unmanned probes on Mars. Each of them weighed 1 ton, the equivalent of a Volkswagen Beetle. A lander carrying humans will weigh up to 60 tons. That's 4 times heavier than what landed on the moon.
And the reason for that is because they have to stay there longer. Once they get to Mars, you're not going to leave in 3 days. You're going to stay there for weeks and weeks and weeks. Plus, you need to bring all the equipment down to help you get back home.
If the heat shield can't slow it down, the 60-ton lander will crash through the atmosphere like a freight train.
If you had a rock and a feather on Earth and you dropped them, the feather would land after the rock. Now on the moon, if you had a rock and a feather and you let go, there's no atmosphere to slow them down, and so they accelerate at the same rate and they fall clunk together. We're doing the same thing at Mars as we'd be doing on Earth, in the sense that we want to make our systems more like a feather. Large surface area and a small amount of mass is more like a feather.
To make them more like a feather, the 1-ton probes used an aeroshell, 3.5 meters in diameter. But a 60-ton human lander would need one 26 meters across, large enough to swallow up 5 bungalows. Now, imagine the rocket you'd need to get something that big off the ground.
There's a limit to how big we can make these rockets, okay? And in fact, you don't want to make a rocket unnecessarily large in diameter just to accommodate this aeroshell. So what we are developing now is an inflatable aeroshell, where you would have a rigid portion like this that's inside the launch shroud, and from it then, after you get out of the launch shroud, you can deploy this inflatable shape.
In Moscow, Valery Fichenko, a thermal protection specialist with Lavochkin Aerospace, is working on the same idea. The Russian heat shield is made of a special mix of organic polymers, similar to the materials used to make Navy Zodiacs, but with one huge difference. To keep the Mars crew alive, this inflatable is designed to withstand temperatures 4 times hotter than molten lava.
Here we use a different substance to cover the material. The substance does not burn away. It evaporates from the surface. While evaporating, it absorbs the heat from the environment and maintains the same temperature.
It's like sweat on human skin, cooling the body as it evaporates. Tests show that this protective layer will only last about 3 minutes, but that's long enough